Ready? Good. Still questions? All right, now let's focus back on active model B. So I hope you got the point that this here has a structure where you have, a gradient of some mobility, which we put here equal to 1, but that's the general structure, so maybe I put it like so. You can make this also into something like that. And then you have the gradient of an effective potential, I would call it a non-equilibrium potential, not a chemical potential, that still has this structure here. So the mu effective is some kind of scalar function as the one we wrote it down here. So this is our mu effective that we have. So it's still that I drive the dynamics by a current that's a mobility times a gradient of a scalar function. Okay, and now you think about this J here, right? This J is actually all you need, right? You need something that gives you a conservation law, and for that you need a vector field that's dotted in a divergence. And this vector field can have this structure, but it can also have a more general structure. Think of thermodynamics. In thermodynamics, you have learned that in general, a vector potential has parts that can be written as gradients of a scalar potential, but not always, right? Vector fields can also have a rotational component, which is very, very important in electrodynamics. So when you think about the most general structure that you can think of for a field theory that's scalar and breaks thermodynamic laws, then the current you can construct more generally. You can make it into structure like so, but also, let me show you this on the slide. So here you see what I did. I wrote, as I just said, this as a minus divergence of a current. The current has the first term, which is a gradient of mu, and the mu is here in the third line. It's the classical phi to the fourth, and the stiffness term minus kappa Laplacian phi. Then we had the other term, which is now the last term, which is also the gradient of a scalar term, gradient of lambda times grad phi squared. That's our term like so. And now look at the middle term. The middle term you cannot write as the gradient of a scalar. So it is genuine something that deviates from this structure of this model that contains scalar terms in the current. And that's called active model B+. For obvious reasons, because it has another term. So people are not very creative in how they come up with names. It's a beautiful model because it has beautiful properties. And for that, let me come back to models that are more on a particle basis. So it's not jump back. We had a picture which is field theories. Now let's jump back and go to particles again. When you have particles, these are the things we learned. So we learned about run and tumble motion. That's what we discussed all along. Things move straight at the constant velocity, they tumble, they move straight, etc. You can also think of a second type of motion where the particles still move at a constant speed, but the direction changes randomly at any point in space and time. Okay? So the direction performs a random walk, but the velocity, the speed itself, is constant. Okay? This is then called an active Brownian particle, whereas the other one is called a run and tumble particle. Now these active Brownian particles, that's something which is not part of the course, but I mentioned it anyway because it's interesting. And I've been talking about this in my earlier lecture, the last semester. So there you have a Langevin equation. X is the position of the particle. I is the number of the particle. And it has three terms that create the motion of these particles. The first one is V naught times a unit vector. That just means particles move at a constant speed given by V naught. The second term is a term that is an interaction term. It's the gradient of a potential. U is an interaction potential between particles, and gamma is a kinetic coefficient. So you have particles moving at constant speed, and they interact with other particles, say by exclusion or by some kind of potential. The last term is a term which we didn't discuss in the lecture yet. It's a random term. It's a term that feeds in randomness in the motion of the particle. So it makes the position a random variable and not a deterministic variable. And eta here is just a Gaussian white noise that adds stochasticity to the motion. The most important term then in the direction is, so theta I is the direction of the particle. And what the second equation says, that the direction performs a random walk. So imagine you have a unit vector on a sphere, and this unit vector performs a random walk on the sphere. And that's the motion of these particles. Okay? And what you should imagine this looks like is the picture here on the right-hand side, something that moves at a constant speed and randomly changes direction as it moves. It's kind of a coarse-grained picture, if you like, from the left-hand side where the runs are of finite length and the tumbles happen only at certain instances in time. When you study the dynamics of these equations, there's quite some literature here. I give you some. And you can study the behavior of these systems as a function of the typical control parameters that guide the motion. Here you see a phase diagram with two different control parameters. One is the activity, so how active this system is in terms of the velocity that these particles have. And the other one on the vertical axis, that's just the volume fraction that you have in the system. And you see when you have a low activity and the low volume fraction, this is a liquid or a gas. If you increase the activity or the volume fraction, you get into a phase that's called MIPS, the one that we talked about, motility-induced phase separation. If you make the volume fraction very high, these systems also have solid phases or hexatic phases. These are particular phases in 2 dimensions that have quite a range of interesting properties like topological defects. And I want to focus on this region where you have phase separation. And here is where the work of Ming Chi comes in. So Ming Chi is a PhD student in the group. He has been studying these motility-induced phase separation problem in terms of active Brownian particles. So here you see again, x and y are the two positions in x and y direction of the particles. This now in discrete form. It moves forward with a certain velocity. There's interaction between the particles. They have a random part in their position. And also they have in the last third line a random part in the direction. Now when you start the simulation, these are really large-scale simulations, you see that these systems show phase separation where you have the blue domains and the red domains. So like in model B, where you have phase separation between high and low density phases, that's something that happens here as well. But there's a more intriguing phenomenon, as you can see. Maybe if you look carefully at the different droplets, they seem to have some surface tension, they round up, but in the interior, they bubble. They have these blue spots that appear from time to time. So it's not a liquid within a gas, it's a gas that contains liquid droplets, and in the liquid droplets there are again gas bubbles. And that's a very unusual and particular phenomenon, which is not there in thermodynamics, and if you have a close-up view, you can actually study the behavior and the dynamics of these bubbles in detail. Okay? And if you want to read about it, Ming-Chi has some archive paper out where he discusses that. And that's an ongoing research theme because it's not fully understood, what gives rise to these bubbles and what their properties are, and Ming-Chi's paper is one that focuses on this question. The active model B+, okay, this is the work by the group of Mike Cates and Cesare Nardini and Els and Jung. They have also found these bubbly phases, not in an active Brownian particle simulation like the one Ming-Chi is doing, but in a model that I already introduced, the active model B+, which is a field theory model that is obtained by a gradient expansion. All right, and it's interesting to compare the two. In what sense is field theory here representing the particle simulations correctly? Are there discrepancies? Is this the same? Is this not the same? These are interesting research questions. But let me come back to the board and just conclude on the active model B, not the B+. So you can do linear stability analysis and you know the solution. Why? The term I introduced anew is this one, and that's not linear. It's a quadratic term. So the linear stability analysis is really the same as the one that we had before. We don't have to do this anew. Okay? So linear stability is as before. So since the lambda term is a nonlinear term. So the initial kickoff of the spinodal, so to say, where phase separation happens, as you saw it in the movie, is the same, independent of this particular term. What's, however, interesting is that the non-equilibrium steady state so the state that you get when you look at long time scales, for that the lambda term is important for the construction of the steady state. And in the problem sets, what you will be guided through is a non-equilibrium version of the Maxwell construction. Okay, so that means not that there's a thermodynamic potential that you can use, but there's something that looks like it and has similar properties and something that you can use to study the steady state. Questions? Okay, let me kind of summarize of what we had. We looked at scalar systems. We constructed field theories. We started out with constructing a field theory basically for a system that has no conservation law. That's our model A. You just have relaxational dynamics. When we continued, we looked at conserved quantities that led us to model B. all in terms of a thermodynamic potential, describing very nicely the field of liquid-liquid mixtures and phase separation. And then we have been moving on towards non-equilibrium systems where we say, let's now take a kinetic point of view and really look at dynamics, which is non-trivial in the sense that the particles that give rise to the collective behavior are no longer Brownian particles, but some kind of active particles. And that has led us to field theories like so. Yeah?
Does mu mean the same thing as a chemical potential in a thermodynamical system?
Not really. So we start out from it, and then it looks like it, and it has a similar structure. So these two terms, they are the same as a thermodynamic object because this is a local free energy derivative, and that's the stiffness term, and this is not. And now in thermodynamics, right, the point is that equal chemical potential is what determines the steady state. And that's no longer the case. Right? And so you lose a very key feature of chemical potential, namely that it's constant in equilibrium. Yep.
Can you say the model there's a blow-up region? I wonder here when we treat velocity has a spatial dependency, then it's possible to also have some blow-up?
Not that I know of. So these equations, so you refer to finite time blow-up, like in the Keller-Siegel model, which is actually a very particular mathematical problem that you face in these systems. Here, there's nothing like that known. And if it would appear, it would be unphysical anyway. Okay?
Yeah.
So then does mu give us any kind of physical explanation of any kind of phenomena in our system?
Yeah, you will see in the problem set you then have to solve the steady state equations, and there this mu appears, and you will have to solve for stationary distribution functions, and the structure of the effective or non-equilibrium chemical potential comes in an important way. But you have to learn anew what these concepts really mean. So what you still have, and maybe I said this wrongly before, so in steady state, you still have that currents vanish in the system, and because the currents vanish, then these brackets here must vanish. So you need to find where gradient of mu is constant. So I said this wrong just a minute ago. But then you have to solve that in terms of the equation that you put in from this chemical potential that you have here. The real difficulty is in getting the Maxwell construction is that in thermodynamic systems you have a second condition, which is equal pressure, equal osmotic pressure that we had. And that's lacking here. So the problem set will deal with the question of how do you construct the analog of an osmotic pressure to then arrive at a condition for the equilibrium steady state. And that's linked with a problem now that you no longer have to minimize a free energy functional, but you really have to solve the equation of motion.